It's my great pleasure to introduce Shari Moskow. She's going to talk about Lippmann Schwinger Lanczos algorithm for inverse scattering problems. And this is our last formal seminar. We've got an informal one tomorrow. That's the gathering together. Please, go ahead.
Thank you. So thank you so much. I want to especially thank the Institute and the organizers of the program for inviting me and asking me to speak and having, it's been great so far. It's not been. So, yeah, so I'm going to sort of describe the Lippmann Schwinger Lanczos algorithms for inverse scattering problems. And this is joint work with Vladimir and Mike, who are here. And yeah, so if you saw Vladimir's talk last week, this is very related. So, but I talk about things from a little bit different perspective.
Shari, do you want me to put the podium for this bit? Are you a bit crushed back? If you're fine, then it's fine.
Maybe up a little. Oops. If I make, maybe I do need you.
It seemed like you were crushed up against the wall slightly. Oh,
Thank you. This should be good.
that's good.
Thanks. So just
Sorry for the interruption.
no, it's okay. That's fine. So first, this is just sort of stating the obvious for the people here anyway, that, well, when you're doing a forward problem, you're given the PDE and the coefficients, find a solution anyway, everywhere, and then the inverse problem, given the PDE data for, well, so this is the kind of inverse problem I'll be talking about is where you're given the solution to the PDE as your data in some form on the boundary for various choices of things like frequencies, times, etc., and find the coefficients. Okay, so I start with that little intro to say, well, reduced order models. So what are reduced order models? So there's a large model reduction community and a large set of literature on model reduction. And for forward problems, the reduced order model is, like, generally think of the PDE or the underlying model for your setting being linear, which obviously doesn't mean that the inverse problem is linear, but that the PDE is linear. A ROM for that problem is some kind of low dimensional system. Vladimir talked a lot about networks, but you could just think of a matrix. It's a linear problem, so low dimensional is a matrix that acts like the differential operator in whatever sense your data is. Well, not for your data, this is forward problems. Acts like the differential operator in whichever way that you want. So what are ROMs for inverse problems? Well, the idea is, and it's relatively recent that they've been used for inverse problems, given data, find a ROM which matches the data and use this ROM to extract the unknown coefficient. So the idea is, in an inverse problem, all you have is the data, maybe some idea about, well, you have some other stuff too, like you sort of know that, for example, you're dealing with the wave equation or whatever it is. Sorry. And so then you can, oh, hi. You can use this ROM, and the idea is that you use the data to get a ROM, and then use the ROM to get the unknown coefficient. So why is this an interesting approach? Because in an inverse problem, in a sense, the most that we know is the data. So if you can find a ROM, so the ROM is essentially a forward model. So if you can find a forward model that when you solve it forward-wise gives you your data back exactly, then that's sort of the best you can do for your forward model in a sense, because it gives you your data back. Okay, so the ROM can also be viewed as a Galerkin method. And this is well known in model reduction theory. On a space of exact solutions corresponding to the data. So if you do PDE Galerkin methods, you're projecting the solution onto a finite dimensional subspace. Imagine that subspace contains the exact solutions which correspond to your data. The ROM would give you that projection. It gives you that system. I'll say more precisely what that is. I don't know if I'm doing this. Oh, sorry. I don't know why. Oh, I just have my cursor in the wrong place. Okay, so after you do that, so you get the ROM, which gives you this Galerkin method. But of course, you don't know the exact solutions. So you can orthogonalize, and this is sort of where the sort of surprise, like, well, sort of, this is sort of why it works. This next part is because if you orthogonalize the basis, localize the basis, the idea being that due to sparsity of your orthogonalization and localization, the basis functions then depend very weakly on your unknown. So you're trying to find the unknown coefficient when you do the inverse problem. If you can find basis functions that depend only very weakly on the unknown, very stably, they move very in a very small amount for as you change the unknown coefficient. Well, then that's good because you don't know the coefficient, but somehow you could get the basis still. And this was first found in a paper by Drexel and other co-authors in 2016. And then, well, once you have good approximation to the basis, you don't know Q, but maybe from some background problem, some background model, you can find the same orthogonalized basis for that model. And if that's not changing with respect to Q, then you have a good approximation to the basis. Well, if you have the operator that projects onto the space and you have a basis for the space, then you have a good approximation to the solution corresponding to your unknown Q. So because we can produce from the data an internal solution, we could use this then data generated internal solution in a Lippmann Schwinger formulation. And so just you write down an integral equation, which you would use to solve inverse, which are frequently used to solve inverse problems. And if we have the internal solution, then if the data gives us an internal solution, then we get a linear equation to solve for the unknown. So that's the basic idea. So I'll first, recent work was done using this in the time domain for a wave speed problem by Borchea and co-authors. So yes, and also, okay, so there's been a lot of previous work before this Lippmann Schwinger Lanczos approach with the internal solution using the ROMs to reconstruct on the coefficients. And so two ones that I'll mention that I won't talk more about, but these gave very nice results. One was in 2018, back projection algorithm, which uses again this fact about the basis being somewhat independent of the unknown Q. And then a later work where they sort of just did some optimization on the ROM itself to find the unknown coefficient. So neither of these approaches, so I'm going to talk about so these were different approaches that worked well too. And then I'll talk about this approach and some sort of new directions it can go. So just to explain the method, I'm going to start by explaining it in the time domain, just so this is a little bit, Vladimir talked about this, so I'll go through this quickly, but it's sort of, I think the easiest, it just has a nice explanation and also sort of shows why these basis functions depend only weakly on Q. So imagine we have a time domain problem like this with some known background, A0, let's just say it's the Laplacian. It will be in all the examples. And you want to reconstruct this Q, our unknown potential. And assume we have some initial source and homogeneous Neumann boundary conditions everywhere on the spatial boundary. There, you can write down an exact forward solution to this problem. It's just with a cosine, an operator of cosine. And then imagine you're measuring data. So your data, we model the data, this G is a source and receiver are co-located at one point, the single input, single output problem. So we can measure the data at the the receiver is co-located with the source, so the data is given by this integral of the solution U against, that's modeled by integration against G. This is a localized function. And imagine we measured at some evenly spaced time steps. And then we could write down the inverse problem, just that given this data F at these evenly spaced time steps, reconstruct Q.
I'm sorry, you mean square root of the plastic?
Yeah. Mhm.
That's the-
No, square root of A, the Laplacian plus Q. It's the unknown operator.
Right, but that's still a sort of differential.
Yeah, right. So you could just think if you discretize it and this is a, this is a, yeah, exactly. So you could define it by spectral theory or think about the matrix version.
It's a bit long.
Yeah, it's not trivial, but we don't actually have to compute it.
Sorry,
Yeah.
just a little bit about 6, because isn't it that operator applied to G and then
Yes.
product with G?
Yeah,
Yeah, so it's not kind of the second brackets X is the result of you doing cosine root A applied to G.
yeah, so there should be a parentheses around that.
Evaluate it.
Yes,
Yeah.
thank you. That's right. I should write that like that. Exactly. That's an operator applying to G.
Yeah.
And that new result is then evaluated at X. Mhm. Exactly. So yeah, so that's important because basically for the following formulas, which are also well known, that imagine you have these true snapshots. So you're measuring at these time steps. You don't know the solution inside the domain, but it exists. So you have some true snapshots inside the domain. You don't know the solution inside the domain, but if I consider this mass matrix or the so-called Gramian in the like the matrix, which is just the integration of these time snapshots against each other, this mass matrix, because of this cosine form of the operator, it turns out all these cosine sum rules apply in the operator form also. And so from the cosine angle sum formula, you see that you can get the entries of M by just some manipulation of the data. This is well known. So it's a cosine angle sum formula, the operator version of it. So you can obtain that directly from the data. Again, we can't obtain the exact snapshots from the data as right now. Well, certainly not the exact ones, but we can get the mass matrix. So this mass matrix is positive definite. So we can compute its Koleski decomposition. And I use U for the upper triangular part. So I have this mass matrix, it's some set of, I think of it as coefficients, and let U, I put this U with a line on it, be a row vector of the first n snapshots. So I can think of each entry in this vector as the continuous time snapshot. Or if I want, I can make this a matrix where the columns correspond to a very fine discretization of each snapshot. Either way, I want to think about it. And then I could use this U if I take the L and the inverse of U and the Koleski decomposition and transform the snapshots. The result will be orthonormal in the L2 norm. And that's just simply the Gram-Schmidt algorithm. So, and it's easy to see that if you take these V's and integrate them against each other, because of the definition of U, it comes out, because of the definition of U, these things all integrate against each other to 0. I mean, to 0 and 1 when it's, the Kronecker delta. So that's just linear algebra. And because this is an upper triangular matrix, going from one to the next is just sequential orthogonalization. It's just the Gram-Schmidt algorithm. I start with the first snapshot at the first time. The next snapshot is a linear combination, is orthogonal to the first. And that linear combination, so that's, and then the third snapshot, I take I find a linear combination that's orthogonal to the other two. Anyway, it's just the Gram-Schmidt algorithm. And that's what used to. So we don't know the snapshots, but from the data, we know the transformation that orthogonalizes them sequentially. So you obviously you can't know the entire internal snapshots, but you know how to orthogonalize. So if you had them, you could orthogonalize them. And it was first noticed in this paper that I mentioned before in 2016, that the orthogonalized snapshots depend very weakly on Q. And I think Vladimir showed a picture of there where we saw that matrix. And if you imagine a matrix and after having reflections, because of causality, the matrix is kind of filled in the upper triangular part. But as you orthogonalize, you lose the part above the diagonal. And you get something that looks very diagonal. And it turns out if you do this for a homogeneous medium versus your perturbed medium, they come out very close. And it's because we start with a local source, orthogonalize sequentially, and the reflections overlap with previous times. So as long as all your previous time snapshots give you a nice basis, you orthogonalize it away, any reflection. So you can do all the above for a known background problem, say the Laplacian. So you have a background exact solution, that's the Laplacian there, square root Laplacian. Background mass matrix, you just compute background snapshots. You can compute its Koleski decomposition. And then you get the orthogonalized background snapshots right here. Well, the crucial step is that the snapshots orthogonalized with Q versus without Q are very close. So because of that, since the true snapshots, you can just kind of unravel it, apply U instead of U inverse, and you get back to the true snapshots. And you assume these orthogonalized snapshots are very close to the background ones. You can the true snapshots are approximately these orthogonalized background snapshots times U. So this gives us a motivation for the definition of our data generated snapshots. And we use boldface they're just this U that you got from the data applied to the orthogonalized ones, which can be written this way. So we have this formula, this U0 inverse U is the transformation from the background snapshots to an approximation of our perturbed snapshots. And then here's a picture of the snapshots. So the blue is the true snapshots. It says cheated, those are the true ones. The reds are the ones we got from this formula here, just from the data. And the yellow is the background. And you can see the red and the blue are very close, where the background's quite different. So the red ones, which are from this formula on this page here, show all the reflections the same way the exact solution does. And so if you believe that so imagine doing time domain Lippmann Schwinger equation. So convert that equation I wrote down into this integral form with a Green's function. And then instead of doing the Born approximation here, we could put this data generated internal solution using this formula on the last page in here. And we got that from the data. And since this is directly from the data, the only unknown here now is Q, and this becomes a linear equation to solve. So that's the method. So that's the method, and now I'm looking at already 20 minutes, so I don't know. So I wanted to explain what happens in the spectral domain, because you can do this in the spectral domain too. And so here, it looks very different, but they're the same. So here we have this sort of the same operator, but now we're in the spectral domain with some lambda. And now the transfer function, instead of looking at time snapshots, we're looking at the function in the spectral domain. And so again, we have source and receiver co-located, modeled by this G. And we integrate on the boundary to get the data that we're measuring. And I just take this particular data set because it's sort of the easiest one to work with, but it doesn't, the data set doesn't have to be in this form. I take the value of the transfer function, or so sort of the integral of the solutions to this equation, depending on lambda, at several spectral values, and also its derivative with respect to lambda. So it's kind of like, becomes kind of like a Hermite type interpolation problem. So imagine that I've gotten this data in the spectral domain, and from there reconstruct Q. So this is the spectral domain version of this inverse problem.
Sorry, can I make sure I understand this problem? So
Yes.
you're really only measuring diagonal elements of the matrix of the nonlinear area, right? So if
Yeah.
It's you know, you take G
Yeah,
and you map it to
absolutely.
you map it to the data that.
Right, so this is the cycle problem with source and receiver co-located, so actually, yes, that's exactly what it is, except I'm not varying G here, I'm varying lambda. So I'm not looking at the whole normative say map, I'm just taking this one. I'm just varying lambda for this one source. For the right now, I mean, this is just to demonstrate, I'm doing the single input, single output for both time domain and just to explain. But all of this works basically in the same way, multiple input, multiple output. But you're right that for the general, and I'll explain more about that later, you do need source and receiver co-located here for this portion of it, at least.
You can still use the polarization identity to get. I mean, if you knew the duplicating on the map with co-located source and measurement.
Okay,
So you
yeah.
get diagonal, but for all values of diagonal, and you can use the polarization identity to get your diagonal.
Yes, we did it for elasticity. You can do any polarization, any polarization coupling.
Yeah.
It would be matrix wise.
Yeah. Okay, yeah, anyway, they're co-located here. So, so given the data, we construct a ROM that matches this data exactly. So, consider exact solutions to this problem. Corresponding to spectral points, like V sub 1 through V sub m. So, then they generate a subspace. So take the span of them. So imagine doing a Galerkin method on them. So you were just going to do Galerkin. So you find the Galerkin matrix. So you just take the variational formulation. You get a mass and stiffness matrix. So this is M and S. Well, you could use it's easy to see. I didn't put this in the slides, but it's easy to see if you look at the variational formulation for these solutions U, and you just add them a little bit. You see, it's very easy to see that you can get the mass and stiffness matrix directly from the data. So again, you don't know the basis you don't know the exact solutions, but the mass and stiffness matrix you can get directly from the data. If you just write down variational formulation, it's really easy to derive that. This is well known. This is all well known.
The diagonal terms are wow.
Sorry?
Diagonal.
Yes, so the diagonal terms are given by the spectral derivative. The derivative in the spectral domain. So I'm assuming I have that data here. Right, and same with the diagonal stiffness matrix. So M and S give us a ROM because it's a Galerkin system, it's a Galerkin projection, it gives us a ROM which matches the data. In what sense what does it mean that it matches the data? It means that if I look at the ROM forward solution, if I had these exact U's and I look for a Galerkin solution, that means I find the coefficients that solve this system. It's just a Galerkin system. Then where this right-hand side is just your data. Okay, so it's just a Galerkin system for the unknown coefficients. If I had these U's, I would have the Galerkin projection onto this space, which should be a good approximation to the solution. In fact, when lambda is one of the given spectral points, it will be exact. So this ROM transfer function, so if you imagine doing a Galerkin transfer function, which is you take the Galerkin solution and integrate and evaluate it at your source receiver, but you know, in the sense of this integral, this f hat matches f exactly. And so we have a, and so it's obvious why at the points, and just, it's not too hard to see why the derivatives match too. But because your exact solutions are in the space, it's exact there. You're projecting onto the space. So, and the derivatives also match. There's a proof of that in one of the papers. So we have the ROM, which matches the data, but we do not know the solutions UI. And we want to localize using orthogonalization like we did in the time domain, so that the basis depends only weakly on the compute. But in the time domain, we were relying heavily on causality, in the sense that when we had the next snapshot, it doesn't go forward faster than the other one. So we didn't have any stuff we didn't orthogonalize out, right? There's no sort of, so we can't orthogonalize spectral snapshots in the same way because they all live everywhere. So instead we use the Lanczos algorithm, and the Lanczos algorithm is Gram-Schmidt using the M inner product, which is just the continuous L2 inner product, on the Krylov subspaces generated by powers of the operator, which is M inverse S, is sort of a discrete PDE here, and initial vector M inverse B. So if B is your source, M inverse B is projecting this onto the space of exact solutions G. And then the new basis A is tridiagonal. This is what happens with the Lanczos algorithm. So the operator is sparse in this new basis, like it is in finite elements. These Krylov subspaces are the same as those generated by time snapshots. Why would we do this Lanczos algorithm? It's because the Krylov subspaces are the same as those generated by the time snapshots corresponding to the ROM. Of course, we don't have the true operator, so we don't know what the true snapshots are, but we do have the ROM. And there's a time version of the ROM. We could do a time version of the ROM. So imagine doing a semi-discretized problem where we keep time continuous. It's like a wave equation. It's the time version of the ROM. So if we kept time continuous and did the Galerkin method, we get this. Well, the solutions of this problem, this semi-discretized problem, satisfy exactly this second order finite difference scheme, where A is M inverse S. So just, do the second order, this different scheme. So these snapshots from this semi-discretized problem are actually give the same subspaces as the Krylov subspaces. So with Krylov subspaces, you keep applying the operator. So you apply the operator, it's not exactly giving you the next time snapshot, but the next time snapshot is a linear combination of the previous powers of the operator. So the subspaces are the same. So if you do Gram-Schmidt, you're getting the same thing. So every time you add a new vector in Gram-Schmidt, whether it's doing time Gram-Schmidt here or doing the Krylov, doing Lanczos, you're adding in the same subspace, the same new dimension, the same new direction. So the Lanczos orthogonalized basis functions are the sequentially orthogonalized ROM time snapshots. So they depend only very weakly on the coefficient. So that's not a proof, I know, but but this sort of explains why. So here's just the one-dimensional spectral. This is an example with 6 spectral values. This is a 1D problem. Here's an example of the basis functions after orthogonalization with Lanczos, and the perturbed and reference medium, and you can't tell them apart. It's cheating a little bit because, these are for positive lambda values. I should point out these are for positive values of lambda, so they're diffuse solutions. So, which makes the inverse problem harder, but, they tend to be, so that, yeah, anyway. So I just wanted to point out, these are first positive values of lambda, so the solutions are diffuse. But this is what you get after orthogonalization, and you can see that they're kind of localized, and as you, this is the first, second, third, fourth, fifth, sixth, and as you get away from your source receiver, they get coarser and further away. So this is the orthogonalized basis, depending weakly on Q. So from the data, we have a Galerkin system, a tridiagonal stiffness matrix, and the mass matrix is the identity. After orthogonalization, things are orthogonal, so the mass matrix is just I. The stiffness matrix is some tridiagonal T for a SISO problem. From the reference medium, we have a highly accurate approximation to the orthogonalized basis. So by solving the Galerkin system, we get the coefficient of the Galerkin projection, and then, okay, so then this is the formula in the spectral domain for this data generated internal solution. These are the orthogonalized snapshots for the reference problem. This is just the scaling you do with the first iteration of Lanczos, and this is the delta. This is the source here after orthogonalization. So that's a data generated internal solution. And here's an example. This 1D example. So again, it's a diffuse. These are positive lambdas, so solutions are diffuse, so they all look the same. The data generated the exact and the reference. But if you zoom in, you can see the reference medium is this yellow, and that's further away. The data generated and the exact are much closer to each other. Okay, so those were just that was just SISO problems, but all of this works for multiple input, multiple output. If you have a lot of sources received, and assuming we have all the data in the assuming that we have all the data in the transfer matrix. So we have taking a spectral domain problem here with a set of spectral values. These are the B's, and then a set of sources. These are indexed by R. And then, so then the transfer function is a K by K block, and I'm assuming I have the full block. So, you know, we model source R at receiver L by integration against GL. Think of it as localized at receiver L. And then, and assume we have the spectral data, again, the derivative and the spectral parameter. And the same, so we get a Galerkin projection on the basis of exact solutions, and the same formulas still hold in the matrix case. And so again, here we can use the Lippmann Schwinger equation. And well, if we were going to do the inverse Born method, we would replace U here by U0. And for small contrast, that works well. But with the data generated ROM, we can replace U by this data generated internal solution. Of course, we have one for each source in this case. So this is like a vector of internal. So this is shorthand, yeah. But yeah. And so, and now that would mean that we can invert a linear equation for Q. So here's an example of spectral domain. This algorithm in the spectral domain, where it's a 1D medium, but I have this is the K equals 2, so a source on each side of the medium, and receivers on both sides too. So it's a 2x2 block system, and this is just the true profile, and then reconstruction from inverse Born and reconstruction from this method. And here's an example of 8x8, again with the full block, and this is this true profile. And this cheated is, so what we mean by cheated is we do the Lippmann Schwinger equation, but use the exact solution for you instead of the one we got from the data. So it's like if you really knew the internal solution for sure. So that's cheating. So that's not really, really, right, so that's the cheated solution, but we like to looking at that as sort of the best we think that we could do. Because if you're gonna, you always, of course, there's the close in this, and again, this was mostly positive spectral values. I think there might have been one negative spectral value in this data set. And this is inverse Born. So this is okay. So this is a relatively small perturbation in the medium. So inverse Born isn't bad, but here's the this algorithm here. And here's a higher contrast. So here this is going up to 2, this one. And here's the cheating again. When you cheat, and again, when you do the cheating, you still have to regularize, right? So here's the inverse Born doesn't work anymore because the contrast is too high. And here's the reconstruction from this method. And again, this is the full data matrix for 8x8 transfer function. So thinking about, like, I guess, geophysics models where you have all your sources receivers on one side, this is 12 source receivers, so K is a 12 by 12 here. And here, if you had the full 12 by 12 matrix, then this is a reconstruction. Again, this is from cheating, this is this method, and this is inverse Born. So, yeah. Okay, but what do we do if we don't have the full matrix? So imagine we had 2 sources and 12 receivers. So the previous versions of the ROM inversion where you were optimizing on the ROM didn't really have a way to deal with that. Like you had to have the full square symmetric matrix. So the nice thing about this is because we're using the Lippmann Schwinger equation, it's a lot more flexibility on which data we have. So suppose we had a 2 by 12 tan transfer function. Just to compare, imagine we had 2 sources, 2 receivers for this problem. The results aren't so good. So if you were to just require that the matrix be full and do the inversion that way, and you only had 2 by 2, this is what you get from this method. And this is what you can get by cheating. So it's not that great anyway. But because we're using the Lippmann Schwinger equation and we have approximations to the internal fields for these 2 sources, we can just put the receivers on the right-hand side of the Lippmann Schwinger equation and just solve it with the extra data. So there's no more work except doing more, a bigger system in Lippmann Schwinger. And we've still sort of made that equation linear by putting these data generated internal solutions. And so here you get a much better reconstruction because you're able to add these other sources, other receivers in. So back to for the time domain. So imagine you're only given the single input, single output responses. So co-located sources and receivers and only that. Well, in this case, we only have the diagonal, not the full transfer matrix. So what you can do is for each source receiver pair, for each separate source receiver, you can construct a ROM for that guy and construct an approximation to the internal solution for that. Now, this is the full, if this is the full 2 or 3D problem, then your internal solution is not going to be great like it is in the 1D case, but you could still do better than just guessing. Or yes, obviously, but then it's still you can do it for each source receiver separately. And then what you can do is take the data from different locations and couple everything in Lippmann Schwinger using the internal solutions for each source. And so here's an example, a 2.5D problem where you assume that the medium is varying in only 2 directions, but solving a 3D PDE. And the model is these 2 inclusions. And here's cheating. So cheating is very good, meaning that we we compute the exact solution to this problem and use that in Lippmann Schwinger and invert that. So that's cheating. So that's bad. And here's if we do inverse Born on this, we get these, echoes, extra echoes. But if we do this algorithm, many of these echoes are reduced here. So this is with the monostatic data. So in our new work, we've been working on still using monostatic data, but doing some data completion. And I'm not sure how this relates to what you were bringing up there, but so if we want to reconstruct an approximate, so we're given again the diagonal transfer function, and let's first reconstruction approximate Q and U using Lippmann Schwinger Lanczos algorithm from above, or some other algorithm from this data. Then you could use the Lippmann Schwinger equation as a forward model using this reconstructed approximate Q and U, and use it to generate your unknown entries of your transfer function. So as a forward model to produce the off-diagonal entries, because producing a Raman internal solutions requires a full transfer matrix, we can use this now. So now we have used this full transfer matrix to do Lippmann Schwinger Lanczos, to do this like sort of a full MIMO inversion. Of course, you only have approximate data on the off-diagonal elements. So, well, sometimes we have to regularize anyway, the mass matrix, but the mass matrix may require regularization to keep it positive, because the off-diagonal entries are not actually the true entries, right? Well, I guess there's always noise, but in this case, you have some significant error because you've used these approximations here. So this is very new, but this is just from the last month. And so this is for a 2D problem, the same profile, but now just a 2D. So it's, and this is the reconstruction with inverse Born. And this is Lippmann Schwinger Lanczos, just the first step with just the monostatic data. And this is using the data completion, which really improved things a lot. So I guess I'm at conclusions now. So I didn't go too long. I guess that was too short. But the mass matrix gives orthogonalization of the time snapshots sequentially in the time domain. But in the spectral domain, we can use the Lanczos algorithm, and then that's sort of bringing things back to the time domain. It's allowing us to do sequential orthogonalization of time snapshots. It's just that they correspond to the ROM, not the true operator. And in both cases, the new basis is close to that from the reference medium. If you have enough data. And we can use the reference medium basis to obtain approximation of the internal solutions from the data. And then use the internal solution in the Lippmann Schwinger equation. So that's the basic framework of everything of this for this method, everything that in this method. So reconstructions can be improved with iteration. And so there's recent work with Liliana Borchea and other co-authors where they've done wave speed. Notice we've done sort of, in this case, in the spectral domain, this is like a Schrodinger type operator. In a wave speed problem, you have other issues with there's some complications due to changing wave speed. And then also the data completion for certain problems where you have only certain kinds of, not complete data sets. So I think that was all I was.
Shari, any questions?
Hi.
Hi.
I was interested in these images. I know I've seen them before, but
Yes.
it's fascinating.
This,
Yeah, so look, maybe you know what someone else knows. Would any of these examples be equivalent to just standard star image formation?
well, I wouldn't say equivalent because it's not from real data, it's from synthetic and it's 2D. And so,
Well, you know, get that standard star image.
yeah, I mean, I don't know, but I mean, this,
It would go the right, left, right, top is border and border.
Right, so if I took I hesitate to say your range profiles
Mm.
and put them with my back projection algorithm,
Yeah, you get border and version.
I get that one right. Okay,
Yeah.
So
oh, I see what your question is. I didn't
Yeah.
understand your question.
that's
Yeah.
okay. Yeah, so you know, you've got plenty of star algorithms out there and images flying around the waves and so on. So the top right is the one. But what do you so that's not intensity or bottom there. It's what is that? It's amplitude that goes negative.
So this,
Oh,
this
this,
is a quantitative reconstruction, right? So it's the same.
it's the potential Q in that equation.
Yeah,
So it's not a star.
no, it's okay, there is,
It's
it's
analogous.
reflectivity. You see, yeah, so it's, Q is reflectivity, so you image your, so if it's, no reflectivity is zero.
Right, okay, so what's negative?
So it can be reflectivity positive or negative, right? Because it gives you negative reflection. Yeah, so it's like,
Okay.
yeah, it's, I would say, we can do also quantitative, but there is like more like qualitative because you can transform, right? You can transform your medium to reflectivity. To, yeah, to just
Okay. Good. So what's the SAR geometry? So is it far field? Is it plane waves?
Well, it's a,
You mentioned SAR, right?
near field. It's near field, it's right on the top. It's near field, sorry.
no, you're fine. Yeah.
So it's
Okay.
near field, and
These are pulses though.
Because you know where I'm coming from, right? I'm in a lab.
Yeah. So it's
So could I say those units on the side are meters?
On the-
Does it matter? Or are they centimeters?
it's in dimension. It's in dimension.
Right.
Yeah, but what's the range of wavelengths?
It's.
Yeah, I don't know. Mike knows. He did.
It's probably around 50 wavelength by 100 wavelength. So 50 depth, 100.
All right. So I guess I could do that.
Yeah, simply,
Yeah.
yeah.
Right.
And just to clarify the spectral problem, how what does that correspond to in physical measurement? So it's monostatic, right? So
Yeah.
transmit and receive in the same place.
Well, in the spectral problems I showed here, I did, it was a full, it was multi-static, it was a full matrix, and the ones I
But
showed here.
that's, in a physical experiment, that would be sweeping the frequency, right?
You would have several frequencies and you could have source and receivers all around the body, for example, and you measure everywhere.
Yeah.
Did I answer your question?
Yeah, I think so. So say if you had a time domain pulse, then
You'd have to
all
just,
those frequencies in it. You'd have to fully transmit.
yeah, right, so I guess it's, right. Right, so it wouldn't be a pulse, you'd have to, right, it's different.
Yeah.
So,
Those raise more questions. So is it one frequency? More questions in my mind. Is it one frequency?
no, this is time domain with a pulse, so it's got
That's many.
many frequencies, yeah.
Yeah, and the frequency domain also cannot do it for one frequency. Few frequencies, but for frequency domain, what Shari showed, it's like in Laplace domain, it's actually worst possible case. It's like it diffuses, it's equivalent to diffusion.
There might have been one negative
Yeah.
spectral value in there, but they're mostly
But
positive.
it mostly
So it's like diffuse imaging,
diffusion optic tomography, basically.
yeah.
The aperture is the top edge, the whole top edge of that.
Well, it depends which picture. In this one, for example, the source receivers are all around the square.
Hmm.
I mean, of course, this is just a model, but.
I find that a bit difficult.
Right, no, yeah, right, but so I guess I mean, maybe thinking about
but
medical
you could-
situations or something.
I mean,
Okay.
like an MDT, non-destructive testing, for
Sure.
example, where you can get all the way around it. Or you,
Yeah.
such as a tree, yeah, we saw it.
I'm just looking at it from the person.
Or building, right? I mean, suppose you have a
Yeah.
building or a bunker or, you know, something that you can't look inside and you're allowed to walk around with. Far as microwaves.
Yeah, but there is, I like to say it again, it's diffusing. Yeah, it's, because actually for,
Stop wavelength image.
it's diffusive, it was
It's
initially easy for us to do diffusive than through wavelength. Now we just do this, but in frequency domain, but.
I do think there was one negative spectral value in this
Right,
data.
okay,
It's
yeah.
not completely
Yeah,
diffused.
for diffusive plus one, frequency like physical. It's maybe artificial, kind of artificial.
Hmm.
Yeah, I see.
I think it's just because we first worked with this in the spectral domain
Yeah,
too,
well, yeah.
so.
We could not really, we had some issue with spectral domain, we figure it now, but if you have in real like, in true like acoustic frequency, have frequency domain regime because we have to shoot with resonance.
Yes.
Right, and now we figured it out, but it was kind of. At
Yeah.
the time we didn't know how to do it, so
Sure.
that we work with it.
Yeah, I understand. So in principle, you could try this with more realistic 2D sound scenario. I mean, this, the basic methodology to.
Yeah, we'll have more examples, more examples. Yeah. So. Of course, main difficulties. That. We use like certain this methods that Shari showed, the extraction. And it can be all these alterations like Galerkin can be done very efficiently that people they have 100+ profits. But we do them like full methods, like, and that's extremely expensive. So we hope we'll have more in University of Lausanne. Will help us. They know how to do this type of problem. But there is a lot of work has to be done, like in linear algebra.
Especially if you want to do it with treatment.
Yeah, so still in freedom, still it's more difficult part of data generation. Because, yeah, so not process.
There's something on the chat.
I think,
Oh.
I think Margaret just said nice talk.
Oh, thank you, Margaret.
Okay.
No, we saw it as a.
Oh, it's not.
Said nice talk. Any more questions? Including from Margaret?
Margaret, did you have a question? Well, I don't want, yeah,
Yeah, right.
put her on the spot.
No, I'm good. I think it's very interesting that the idea that you can see which artifacts might be changing as you do this, and that gives you a clue as to what the correct reconstruction is and which things might be artifacts. And it's very interesting. I'm glad somebody's doing some iterative processes.
I think it's the multiple scattering, like that's mainly what this does, I mean, compared to boron.
Yeah, because it's full wave, right?
Right, it's full wave.
What about ultrasound then? Because we
Yeah.
earlier in the program, we saw some really nice work on ultrasound tomography reconstruction, not travel time, but actual full wave reconstruction for sound speed, right?
Yes,
And attenuation.
yes.
Yeah, and last week, right?
Yeah, exactly. Last week's talk too. So I think we were talking to him, but so there's a paper from, I think 2018, where Maminon and others applied to ultrasound models, the ROMs, not Lippmann Schwinger Lanczos, but using the back projection algorithm that I mentioned here. but still using the fact that these basis functions are weakly dependent. So, but that was a sort of the previous,
Yeah, yeah. I mean, they were doing full wave reconstruction.
oh, it's full wave,
for
yeah,
Medical imaging.
yeah. And they have really nice picture, I mean, really nice results with that,
It's
yeah.
like the computers just got big enough to do it, really. So
Is
they
that,
just
yeah,
have to get cleverer, so.
yeah, I'm not familiar with what the limitations are in the lab setup, which are obviously a big thing, but yeah, I think that the models they did, they got really good pictures of, you know, we were looking at that together, was it yesterday? Or the day before, yeah,
And we also have like first results with have a paper also with Jordan and Juliana, and then also new results with Lippmann Schwinger for loss unity when you have
Yeah.
dumping, because also we can image
Yeah.
the dumping.
Yeah, which was the case for this ultrasound medical tomography.
Yeah, yeah,
right?
so-
They get the real elementary.
So it's all possible.
we went to prove something about, more about the basis, because
Yeah.
there's a lack of. I mean, we need more rigorous results there.
Okay, there's no more questions. Thank you.